Hello everybody, this is a quick video. It's actually not so quick video on what betas are and how they're used in fNIRS. So in this example, we're going to talk about finger tapping tests, mainly because it's a very simply understood test. Basically, what happens in these types of experiments, you have a subject, you set their cap up, you introduce them to the experiment, usually with a screen that tells them, welcome to the finger tapping test. When the screen says left, tap your left hand. When the screen says right, tap your right hand. When there's nothing on the screen or when there's a little crosshair on the screen, don't do anything. Each of these, it will be repeated a number of times determined by the researcher. For our sake today, each condition will have 3 trials just to get a little average, but you could do 5, 10, 15, however many trials you needed for your experiment. What this looks like as a time series is basically this. We have about 220 seconds of data here. And we have 2 data streams coming in. These are each wavelength of data for a channel mean. So it's all channels averaged together. It doesn't tell you that much information, but it gives you an idea of that there's data coming in. These pink bars are basically when the hands are being tapped. So first it starts left hand and it taps for a period of time. Rest, right hand, left hand, right hand, left hand, right hand. And the spaces in between are all rest periods to allow the response to return to baseline. Once you have that, you're going to want to model your data. And what a lot of people don't realize is that you often model data without even realizing you're modeling data. The simplest model is simply a mean. A mean value for a channel would technically be a model, but it's a very shallow model. You don't get much information. You just get one number for that channel, for that condition. Another slightly more complex version would be a line. So you can model your data just using a line. You can say, oh, the slope is up, oh, the slope is down over this time period. Again, it gives a little bit more information than the mean, but not much more. I like to think of models as something of a filter, or also a mask, which I'll talk about in the next slide or two. A filter saying, okay, I have a circle here on let's say on an image. There's an image here. I only care about what's inside this circle. I'm going to look at everything here. I'm going to ignore everything out here. I'm going to filter out all that. The other idea would be a bandpass filter. You have frequency here, a frequency here. I only care about what's in here, and I'm going to ignore everything on either end. So each of those is a filter. In our case, we have the canonical hemodynamic response function. And what you can look at here, this is what it looks like. I basically care about what's related to this line. So in a sense, it's a filter. It'll basically view my data within this. I'm really concerned about this kernel, you'll say, of the data. The canonical hemodynamic response function, or HRF, is widely used in fNIRS and fMRI, and it's pretty much the standard go-to for any type of response model. So you would actually use this based on some knowledge, usually some research, some pilot studies, something that you received this model from, and this is what you expect your response to look like. So the standard is over here on the left. You'll see it has a peak value of around 6 seconds. It drops back down and overshoots the baseline to about 15 seconds, and it flatlines after that. But let's say we expect our data our response to be delayed. For some reason or another, we don't expect a response for 12 seconds. Well, this over here is actually the exact same model, and you're going to see parameters up here on the right. This first parameter went from 6 on the left to now 12, and the peak value went to 12. So all it did was actually shift really my area of interest, we'll call it, to about the 12-second mark and a little bit around that. And you'll notice it starts from over here, we're at 1 or 2 seconds, up to about 11 seconds. This is kind of my area of activation I'm interested in. Over here, we have 6 seconds all the way up to about 17 seconds. That's my area of interest I have over here. And just as I said, it's a filter or it's a mask. I like to think of this as a temporal mask or a timing mask. I care about a certain window of time. And the reason I say that is because let's say we have activation over here at 25 seconds. Well, I'm going to basically, that doesn't help me at all. It doesn't state that my data fits this model. It doesn't state that this is activation based on my task. So I like to think of it as a temporal mask of sorts. Once you have the model, you actually put it into something called a design matrix. The design matrix will now take into account time. So it doesn't just take your model into account, but it actually takes now your time into account. And you'll see here we have model 1, that's the left hand, model 2 is the right hand. It's actually the same time series on both, and you notice the red line, which is the channel average data, again, not very helpful, but it shows you data is coming in, is identical on both. The first thing you'll notice is we have these blue rectangles. These are the boxcars. Boxcars are actually a type of model. You can model your data using a boxcar, but because they're so sharp in shape, it's not very similar to a hemodynamic response. Basically, if a hemodynamic response is a slow pump that undulates, whereas a boxcar is more like a light switch that turns on and off. What you do see, though, is here on the top, I tap my left hand during this period, and I turn off. And then I come down here and I tap my right hand and I turn off, and left, then right, left, right. Then this green line actually is the model, and that's overlaid onto the boxcar. If the boxcar stretches wider, if I tap my fingers for longer, the model will be stretched wider. If I do it shorter, it'll be shorter. The mathematical term for this is convolving. Basically, you're taking both of these, the boxcar and the model, and you convert them to the frequency domain, and you multiply them out and then convert back, and you get a convolved model. I like to just say they're overlaid, because that's basically what it completely appears to be. What you see on the right is actually the same information, but in a more simple format. The first column's the left hand finger tapping, the second column's the right, and these white bars are actually when the model peaks. And what you notice is just following the white bars is an even darker shade of black, which is this dip, this overshoot after the model returns to baseline. And again, you go left, right, left, right, left, right. There is a third column, which is known as the control. The controls, I've actually never seen it used, but it's there to basically regulate, as is what I've been told. So once we have the model, once we've created the design matrix, we have to figure out, eventually we're doing statistics on these beta values, and a lot of people don't know or understand what these beta values are. And I think they're needlessly complicated. So going back to basic algebra, you have the line formula. If y equals mx plus b, well, just as I mentioned, a line is a model. You can actually model data using a line. So we have a very basic model, y being the output, m being the slope, x being the input, and b being the y-intercept. For our sake today, we ignore the y-intercept. We're just going to throw that out. But this m, the slope of the line, is the very basic version of beta. If it's negative, it's a negative relationship. If it's very positive, it's a very positive relationship. Moving into statistics, it's been complicated a little bit more, but it's still the same idea. Basically, now we have y hat, which is our model, our design matrix. We have beta naught, which is now they've taken the y-intercept and moved it to the front. But it's just the y-intercept, and we're going to pretend it's 0 for today, so we ignore it. Then we have beta 1, x1. Beta 1 is the first beta we're going to look at. X1 is my data matrix. So that's actually kind of where the bulk of the meat is. Then we have this error term that's just always stuck there, and we'll ignore it till the end. But that, just keep in mind, it's always there. So in the line formula, you were just dealing with slopes, rotating a line. The greater the slope, the greater the value. Well, this is a shape, and you can't slope a shape. It doesn't make sense that we're sloping a shape. We're actually going to be picturing it as stretching or shrinking. And so just as though the line was raising in slope, the shape will essentially be growing or shrinking. And again, we're going to assume that beta naught, or the y-intercept, is 0 for this. So the question is, though, how do we solve for beta? Well, it's basic algebra in this case. We got rid of beta naught. We're going to pretend the error is not there for now, and we'll just kind of add it back in. But what you're going to do is just divide by this x1, move it over here, and now you have a formula for beta 1. Great, that's great, but that's not really what you're doing. You'll actually be doing it's something a little bit more complex than that. But that's the idea. It's a very simple, straightforward idea. So the beta you can consider as kind of a weight. It's just like a slope. The larger the value, the more relatable it is to the model. The lower the value, the lesser related it is to the model. But we got that error term. So the big question is, how do we decrease the error term as much as possible without removing ourselves from that a priori model, that a priori shape. So this is done through ordinary least squares, and or a version of ordinary least squares. There's a few out there now. And the idea is that we're going to solve for this and at the same time reduce that error term as much as possible. So why do we actually do this? It's, you couldn't just use a mean value. Why not just use a mean value? If a channel was more active, it would have a greater mean value in that active activity. Well, looking at these two responses to finger tapping, this is kind of what I'm trying to explain here. So this first one has a nice peak value around 6 seconds. It returns to baseline around 15, 16 seconds. There's a nice overshoot at the end. The second one doesn't hit a peak value till about 14 seconds. And it's at about 5 or 6 seconds, it's actually almost at zero. It may be 1 to the -4th. So which one of these is likely more related to the task at hand, the one that started at this vertical pink line? Well, if we look at the model and we consider the model to be accurate, the one on the left, it fits the model exactly. There's almost nothing around it other than the heart rate that we haven't filtered out. So the one on the right, I would assume actually is more ambient brain activity, brain activity that had nothing to do with the task since it took so long to respond. It could be peripheral information. It could be just the brain wandering. It could be, lack of focus or something that caused a later delay. The other thing worth noting is this looks to be even a little bit of noise here, and I say that because both the deoxy and oxy move in the same direction at that moment. So that's the reason you use the model. If there's activity delayed in your window, but you're still considering it identical to the activity that would be in direct response to your task, that's not accurate. You want things that happen due to your task, not things that happen just because the individual is tired or the individual had a rough night or something like that. So once we extract these beta values, we solve for beta, we decrease the error term as best we can. We have this value now. Question is, what does that mean? What do we do with it? So each channel, we're going to focus on one channel, noting that you're going to do this on every single channel individually. Each channel has, in this case, 2 betas. The beta is going to be for each condition. We have 1 beta for left hand, 1 beta for right hand. And you're going to compare the tasks. So I want to see, does my left hand finger tapping on that channel, is that different than my right hand finger tapping? And you're going to do that using a statistical test. Usually that's going to be, in the case of finger tapping, a t-test. It's because you have 2 conditions, straightforward, you compare them against each other. If you have more than 2 conditions, you would likely use an f-test. The f-test, I had a colleague explain this to me, I think, better than anybody. The t-test is asking the question, does A equal B? Does left hand equal right hand, or is it different? The f-test is asking, does A equal B equal C equal D, as many as you want. And basically it's going to say if any one of those things in the link are different, it's going to give you a positive result. So it allows you to compare many, many, many tasks against each other, but it doesn't tell you much more beyond that. So we're going to start with a t-test, and we're going to start with a contrast, which we'll actually use for both, but specifically the t-test. So in the background, when you go to do this, you're going to actually get all the beta values for all the trials, and you get that average value. Then you're going to have the standard deviation for those as well. So beta values for left, standard deviations for left. Beta values for right, standard deviations from right. Then you're going to actually create a contrast, and the contrast is based on this design matrix here. You notice we have 3 columns, 1, 2, 3, and I have left and right just to designate that. So here I have 3 columns. If I leave this all as zeros, it doesn't tell me anything, no information. If I want to compare the left versus the right, I multiply the first column by 1, the second column by -1. So I get 1, -1, and 0. I can invert that if I wanted to, but basically what it's going to tell me is what was greater in my left hand than my right. If I flipped it, it would be what was greater in my right hand than my left. And you can also just do 1, 0, 0. That would just tell you what is the beta value, or sorry, what is the difference between my left hand versus no activity at all. In calculating it, the calculation is pretty simple. You calculate the mean of the first column, which is the left hand, mean of the second column, which is the right hand. You subtract those, and then you divide that by the square root of the standard deviation of the left hand over the number of samples, which will be the trials in this case. Then the right hand over the same samples. So that looks like this. You have mean 1 minus mean 2 square over the square root of standard deviation 1 squared over the number squared, or the number, plus the standard deviation of the second column squared over the second number. Oftentimes you'll subtract 1 given the for a conservative measure rather than a straightforward measure. It tends to be more appropriate. What that gives you, that t-test will give you a t-statistic. The t-statistic will compare that channel for each task. So this channel for my left hand versus this channel for my right hand. And you do that for every channel across the head. So a larger positive value will indicate that the first column, or the positive contrast part, was actually greater than the second. A negative value would be the opposite. To figure out which one is what's actually significant, you'll get a value, but is the value significant? You would need a p-value associated with that. Most softwares will automatically print the p-value with it, but oftentimes you'll actually have to Google a t-stat table, and you can look that up. And you look up the number of trials and the t-value you got. So moving in from t-test, you have the option of an f-test. And the reason you'd want to use the f-test, again, is if you have more than 2 conditions. So if there are only 2 conditions, you could still just do an f-test and you get similar results to a t-test. It really doesn't matter, but a t-test is pretty straightforward. And the advantage to the f-test basically tells you, is there a difference at all? Doesn't tell you where it is. Doesn't tell you what aspects are different or in what way they're different. Just, is there a difference? I added a little column here. So now we have left hand, both hands, and right hand. So now we're actually trying to see, is the left hand any different than both hands, or is that any different than right hand? And what we have now is 3 conditions: left, both, right, and control. So 3 plus 1, 4 columns. And I can actually contrast multiple contrasts at once, all in one go. And what we have is the first contrast is 1, -1, 0, 0. That's the left hand compared to the both hands. The second one is the left hand compared to the right hand. And the last one is both hands compared to the right hand. So again, this will tell me whether or not there's any difference at all, but it will not tell me what the difference is. So the calculation is a little bit not as straightforward as the t-test. The t-test is you're comparing mean values and you're standardizing them. I think that's the basics of statistics in most cases. The f-test, you're comparing variation. Specifically, you're comparing the variance between the tasks. So I'm comparing the variance of the left hand versus the variance of the right hand versus the variance of both hands. And I'm comparing that, or I'm dividing that by the variance within each. So is the variance between the conditions greater than the variance within the left hand? Is the variance between the conditions greater than the variance within both hands? Is the variance between all the conditions different than the variance within the right hand? So this allows you just, is there an obvious difference between these? The output you'll get is an F statistic. And the difference between a T statistic and an F statistic, T stats can be negative. F stats are 0 and larger. It will tell you the larger the value, the more the difference, but it doesn't tell you what direction that difference is. Was left greater than right or right greater than left? It won't tell you that. And again, you'll need a p-value to know how sure these values are. And I put sure in quotations. Again, any software used will likely calculate the p-value with you or with it, or you can look up an F table. So finally, we have a difference. Your F-test shows significant results. Great. What's significant? So after you conduct the F-test, you will likely have to do a post hoc test. And usually this is a t-test, which is corrected for multiple comparisons. We won't go into detail on that, but oftentimes it's family-wise error rates, corrections, or things like that that you can find. And again, you usually can find a software that will automatically conduct those for you. So in summary, I think this is kind of a very straightforward way to state this, but also it's a little bit of a lie, but it should leave you with a good idea of what these beta values are. So a beta value is very similar to a slope of a line. The greater the slope, the greater the value, right? The difference is that we're not dealing with a straight line. So you can't just increase slope. You actually have to increase a shape or decrease a shape. So overly simple, but here it is. On the left here, you see what would be deemed a small beta, very small bump. So that would say there's little activity. There you can. The next one in is a medium beta. There's some activity, and then the big beta. There's a whole bunch of activity. So if you were to compare these across, the big beta would be shown as more active than the small beta. You can also have them negative, and they'd be flipped upside down, and that would be obviously a deactivation or a decrease in activity. Anyway, I hope that was helpful. It should give you a pretty good understanding of what these betas are, what you're actually doing when you compare these, and why you would actually use them.